Welcome to Vertex, the channel where we explore the mysteries of space, science, and the future of our cosmic story. Tonight, we dive into one of the rarest events ever recorded. A moment when something from another star system, something older than our sun, swept past Mars and changed everything we thought we knew. Stay with me, because what you're about to hear truly happened. What if something from another star system changed Mars forever? And we're only now beginning to understand what happened. For the first time in recorded history, an object born in the darkness between alien suns swept past the red planet at a distance so close that every major space agency on Earth held its breath. This wasn't just another flyby. This was an encounter that defied probability, challenged our understanding of planetary interactions, and left behind questions that still haunt the scientific community today. The visitor's name was 3I Atlas, and what it did to Mars might have rewritten the rules of our solar system in ways we never imagined possible. You're about to discover evidence that scientists are still analyzing. Mysteries that refuse simple explanations. And a cosmic event so rare that some researchers believe we won't see anything like it again in our lifetimes. Stay with me. In the next few minutes, we're going to explore the most unprecedented interstellar encounter Mars has ever experienced. What happened during those critical hours? What changed in the Martian environment? And what it all means for our understanding of how worlds can be touched by visitors from the vast cosmic ocean beyond our sun. If you've ever wondered whether a single object from another star could alter the fate of an entire planet, you're in the right place. Hit that like button right now and drop a comment telling me what you think really happened when 3I Atlas swept past Mars. Because what I'm about to share with you will challenge everything you thought you knew about planetary encounters. Imagine standing on the surface of Mars beneath a salmon-pink sky. Dust devils twirling in the distance across ancient valleys that once held oceans. The thin atmosphere whispers against canyon walls carved by water that vanished billions of years ago. Everything feels timeless, unchanged, locked in a geological sleep that has lasted longer than human civilization has existed. Then something appears in that sky, something that doesn't belong, something that was never supposed to be there. An interloper from beyond, carrying the chemical signature of another star system, moving on a trajectory that speaks of origins so distant that light from its birthplace hasn't reached Earth yet. This is the moment when Mars met 3I Atlas, and nothing about this encounter was ordinary. The date itself felt surreal to those tracking the comet's path. Scientists had calculated the trajectory weeks in advance, running simulation after simulation, triple-checking the numbers because the odds seemed impossible. Comets from interstellar space are rare enough. We've only confirmed a handful in all of human history. But for one to pass this close to a planet in our solar system, the probability calculations made veteran astronomers shake their heads in disbelief. Some researchers later admitted they kept rechecking their work, convinced there had to be an error somewhere in the orbital mechanics. There wasn't. The universe had arranged something extraordinary, and Mars was about to experience what no human eye would ever directly witness. An intimate encounter with an object forged in the cold darkness between stars, carrying ice and dust from a stellar nursery we can only dream about. What makes this moment so profound isn't just the rarity, it's what it represents. Think about it. Every atom in your body, every molecule of air you breathe, every grain of sand on every beach on Earth was born either in our sun or in stars that died before our solar system formed. We are made of stellar material, but that material has been processed, melted, reformed, and integrated into the fabric of our cosmic neighborhood for over 4 billion years. Everything around us shares a common heritage, a common chemistry, a common story written in the language of solar system formation. But 3I Atlas, it carried a different story. Its ice froze around a different star. Its dust condensed from a different nebula. The organic molecules within it, and scientists suspected there were organic molecules formed under conditions we can only theorize about. When this visitor approached Mars, two entirely separate threads of cosmic history were about to intersect. The hours leading up to the closest approach created a strange tension in observatories around the world. You have to understand what this meant for the teams tracking the encounter. These weren't people prone to hyperbole or sensationalism. These were men and women who had spent careers studying orbital mechanics, atmospheric chemistry, and planetary science with the kind of patient precision that defines modern astronomy. They deal in facts, measurements, spectra, data. And yet, even among these professionals, there was an undercurrent of something that felt almost like anxiety. Not fear nothing about 3I Atlas posed any threat to Mars or Earth, but rather the weight of witnessing something that might never happen again. The pressure to capture every possible piece of data, to miss nothing, to ensure that this fleeting moment would be preserved in the permanent record of human knowledge. Because here's the truth that kept everyone awake during those critical tracking windows. If we failed to document this encounter properly, future generations would never forgive us. Mars itself had no awareness of what was coming. Of course not. The planet continued its eternal rotation. It's a thin carbon dioxide atmosphere cycling through seasonal changes. Its polar ice caps expand and contract with the Martian year. Dust storms swept across the equatorial region, some small and localized, others massive enough to engulf entire hemispheres. The planet's two tiny moons, Phobos and Deimos, continued their rapid orbits, casting swift shadows across the rust-colored landscape. Somewhere in the ancient riverbeds and crater floors, the Curiosity and Perseverance rovers went about their programmed tasks, drilling samples, analyzing soil, searching for signs of ancient microbial life that might have thrived when Mars was young and wet and warm. The planet existed in its routine, unaware that something unprecedented was approaching from the direction of the outer solar system. Inbound on a hyperbolic trajectory that would bring it closer to Mars than many of the planet's artificial satellites. The magnitude of what was about to happen becomes clearer when you consider the distances involved. Space is vast beyond human comprehension. Even within our solar system, the gaps between worlds are enormous. Mars orbits the Sun at an average distance of over 200 million kilometers from Earth. Interstellar visitors like 3I Atlas travel through the solar system on paths that usually keep them far from planetary encounters. The geometry alone makes close approaches statistically unlikely. Planets occupy tiny fractions of the solar system's volume. For an interstellar object to pass close to a planet requires an alignment of trajectory and timing so unlikely it borders on the miraculous. And yet here it was, happening in real time, with the entire astronomical community watching. What did those watching expect to see? The honest answer is, nobody knew for certain. Previous interstellar objects had given us clues: unusual outgassing patterns, unexpected brightening, chemical signatures that didn't match solar system comets. But every prediction came wrapped in uncertainty because the sample size was so small. We had barely begun to understand these cosmic wanderers, and now one was about to interact with a planetary environment in ways we could actually measure. Would 3I Atlas shed material into Mars' thin atmosphere? Would it change the planet's exosphere, that fragile transition zone between atmosphere and space? Could there be electromagnetic effects interactions between the comet's plasma tail and Mars's weak magnetic field? The questions multiplied faster than anyone could form hypotheses. Some researchers allowed themselves to imagine more dramatic possibilities, though always framed carefully as speculation. What if the encounter triggered changes in Mars' atmospheric chemistry? Temporary disturbances, subtle alterations, something instruments might detect. What if dust or gas from 3I Atlas actually reached the Martian surface, leaving behind molecules forged around another star system? Imagine collecting samples from Mars years from now and finding traces that originated beyond our sun's influence, deposited during one brief cosmic moment. The closer the 3I Atlas came, the more the tension built. Observatories synced their schedules, ensuring continuous coverage across multiple wavelengths. Radio telescopes listened for unusual emissions. Spacecraft orbiting Mars received new instructions. Every telescope that could be spared turned toward the space between Mars and the approaching visitor. Humanity had become a global mission control, not for a spacecraft we built, but for a cosmic event we had absolutely no control over. Then came the moment of closest approach, measured not in millions of kilometers, but in distances so small by astronomical standards that they almost defied belief. For a brief window of time, 3I, Atlas, and Mars shared the same region of space, close enough that gas and dust from the comet would definitely intersect Mars's path. Close enough that Mars's gravity, though weak, would measurably bend the comet's trajectory, changing where it would travel next, and where it might wander in the galaxy for thousands of years. What happened during those hours? The full picture would take months to piece together, but even in real time, observers knew something significant was unfolding. The comet brightened slightly, a sign of outgassing as solar heat vaporized ancient ice. Dust and gas spread along the comet's orbital path, material frozen before our sun ever existed, now drifting across space near Mars. As Mars and 3I Atlas converged, the comet's tail swept through the region the planet occupied. Did molecules from 3I Atlas touch Mars's atmosphere? Did dust grains forged around another star drift into the Martian exosphere? Instruments captured data. Spectra were recorded. Photons carrying information from another star system were being collected in real time. But what it all meant? It would only be understood months later. There's something profoundly moving about this. Mars, a world that has existed for 4 billion years, had never experienced anything like this. A visitor from beyond, a touch from a completely different cosmic lineage, a handshake between worlds that formed under different suns. If Mars could speak, what story would it tell about the moment 3I Atlas swept past? Researchers watching understood this weight even if they couldn't articulate it yet. They weren't just observing an orbital event, they were witnessing a meeting of histories. The discovery that the 3I Atlas would pass so close to Mars didn't happen in isolation, and the global response certainly didn't come from a single agency working alone. Within hours of the refined trajectory calculations, a cascade of communications spread across 3 continents: NASA's Jet Propulsion Laboratory in California, the European Space Agency's Operations Center in Germany, the China National Space Administration's Deep Space Tracking Network. All of them recognized the same truth. This was an opportunity humanity might never get again. The usual barriers between agencies, political, logistical, bureaucratic, dissolved almost instantly. Everyone understood the stakes. Everyone understood the timing. Everyone understood that the universe doesn't schedule rare events around government budgets or administrative delays. And yet, at the very moment when unity was needed most, NASA was operating under severe constraints. A partial government shutdown had slowed internal communications, limited resources, and placed enormous pressure on mission planners. But here's what makes this moment legendary. The universe didn't care. So NASA's people did what they always do. They found a way. The European Space Agency stepped up immediately. Mars Express, their veteran orbiter, became one of the backbone instruments for the encounter. Engineers rewrote command sequences overnight. Instruments were retargeted, recalibrated, and reassigned. CNSA joined with equal force, offering access to its deep space tracking network and contributing models built by Chinese astronomers who had been studying the 3I Atlas since its discovery. Suddenly, what began as a scientific alert had become a global choreography, a coordinated effort stretching across nations, languages, institutions, and time zones. And the true heroes? The mission operators, the engineers, the scientists behind consoles and code. They had one chance, one window, one moment when the Comet and Mars would align in a way that would never repeat. Miss it, and the data would be lost forever. Capture it, and humanity would record one of the rarest events ever witnessed. NASA's MAVEN orbiter, built to study Mars's upper atmosphere, suddenly became the perfect instrument for detecting whether material from 3I Atlas reached the planet. Its ultraviolet spectrograph could detect hydrogen atoms at unbelievably low concentrations, the signature of vaporized cometary water. So engineers scrambled to reconfigure MAVEN's instruments. Every parameter returned. Every scanning sequence is adjusted. If even a whisper of interstellar hydrogen touched Mars, MAVEN would hear it. The Mars Reconnaissance Orbiter, designed for ultra-sharp images of the Martian surface, received new commands as well. Its cameras, normally pointed down at canyons and craters, were redirected upward, toward the dark sky, toward a tiny moving smudge that was 3I Atlas. The MRO team calculated every factor: thermal limits, power draw, exposure times, pointing constraints, antenna windows, spacecraft orientation. Everything had to be perfect. One miscalculation, one mistimed rotation, one faulty sequence, and the opportunity would be gone. ESA's Mars Express contributed a different vantage point. Its stereo camera provided the second angle needed to reconstruct the comet's approach in 3 dimensions. That dual-view geometry would later prove essential to understanding how 3I Atlas's material intersected Mars's atmosphere. Meanwhile, on Earth, a relay of ground-based telescopes spanned the planet. Chile to Australia, Australia to Hawaii, Hawaii to California, California to Spain. Spain went back to South America. A 24-hour observation loop. Humanity is watching, literally non-stop. Professional astronomers joined amateur observers. People with backyard telescopes contributed brightness data, tail evolution data, and orbital correction measurements. Everyone who could help helped, because everyone understood the same thing. This was history. And as the moment approached, the tension inside the mission control rooms across the world was electric. Engineers hovered over telemetry streams. Scientists stared at preliminary plots. Data analysts sat ready to catch the first incoming packets. Every station, every team, every instrument was in perfect alignment, not by luck, but by effort, by expertise, and by the refusal to let this moment slip away. Then it happened. The first data packets from MAVEN arrived. A slight elevation in hydrogen, subtle but real. Then, MRO images trickled in faint, blurry, raw, but unmistakable. 3I Atlas, captured near Mars. Mars Express confirmed it from another angle. Ground-based telescopes confirmed brightness changes. Radio telescopes detected shifts in plasma emissions. In just hours, researchers had gathered more data than anyone had dared to hope for. The instruments worked. The coordination succeeded. The universe cooperated. Humanity had documented a once-in-a-million-years moment. A visitor from another star system is interacting with a planet we've been studying for decades. And the data? It was beautiful. It was overwhelming. It was historic. The images came in quietly. No dramatic alarms, no cinematic countdown. Just raw photons captured millions of kilometers away, transmitted across deep space, arriving as lines of code on computer screens. But for the people watching, those first images were everything. They represented proof. Proof that humanity hadn't wasted the moment. Proof that the universe had allowed us a glimpse into something rare and magnificent. Processing the images wasn't glamorous. It wasn't instant. It wasn't easy. Astronomers spent hours removing noise, adjusting pixel sensitivity, stacking exposures, compensating for spacecraft motion, coaxing clarity from what first looked like static. And then, as if emerging from fog, 3I Atlas appeared, a faint, glowing smear against the backdrop of stars, soft edges, a visible coma, the beginning of a tale. For the scientists who had been tracking this interstellar body from the moment it was discovered, this wasn't just data, it was emotional. The thing they'd modeled, plotted, debated, and prepared for was now on their screens, suspended in the same field as Mars, a visitor from another sun, passing our cosmic neighbor. But the real revelation came from MAVEN, because MAVEN wasn't looking for images, it was listening to atoms. Its ultraviolet spectrograph detected hydrogen emissions, that did not match Mars's natural atmospheric baseline. No noise, no errors, not an artifact. But new hydrogen that wasn't there before. Hydrogen that peaked precisely when 3I Atlas's coma crossed above Mars. This meant something extraordinary. Hydrogen atoms from another star system had reached Mars. Atoms born around a different sun, atoms that had been traveling alone through interstellar darkness for millions of years, had now brushed the atmosphere of the red planet. This wasn't a theory. It wasn't speculation. It was a measurement. Recorded. Confirmed. Real. And hydrogen wasn't the only guest. MAVEN detected subtle increases in oxygen and even carbon, likely broken free from cometary ices and organic molecules. These particles were tiny. Their concentrations are microscopic, but their meaning, enormous. Because it meant that Mars had been touched, chemically, physically, by a world from beyond our solar system. The images revealed more. The coma shape wasn't symmetrical. The tail wasn't uniform. There were active jets, patches where 3I Atlas was releasing more dust and gas than others. This complexity pointed to internal structures within the comet. Volatile pockets, caverns, surface fractures, just like other comets we've studied, yet distinctly its own. Meanwhile, Mars Express provided the second angle that allowed scientists to map the geometry in 3 dimensions, confirming exactly where the comet's gas cloud overlapped with Mars. Every perspective, ground-based, orbital, ultraviolet, visual, all told the same story. Material from 3I Atlas had interacted with the Martian environment, not theoretically, not indirectly, but in measurable, documentable, physical reality. This discovery rippled through the scientific world. Research teams rushed to publish early findings. Data sets were shared across borders. Press releases went out. News outlets picked up the story. For a brief moment, the world looked up, captivated by a cosmic event that had happened quietly above a world millions of kilometers away. But the scientists weren't captivated. They were focused, driven, determined, because they knew something the public didn't. This data would define years of research. The real work had only just begun. The encounter with 3I Atlas didn't just reveal something about the comet. It revealed something about us, our readiness, our cooperation, our ingenuity. It showed that even during political tension, funding issues, or global distractions, humanity can still unite in the pursuit of cosmic understanding. But the most profound realization came from the hydrogen signature itself, because it meant this: Mars now contains material from a different star. That is not poetry. That is not a metaphor. That is chemistry, documented, measured, preserved. Atoms from another sun, now part of the Martian sky. The first confirmed interstellar planetary chemical exchange ever observed by humans. And it happened in our lifetime. Mars's atmosphere is thin, but it is not simple. It is layered, fragile, dynamic, a ghost of the thick, warm air the planet once had. And when 3I Atlas passed near Mars, it was the uppermost layer, the exosphere, where the encounter left its most measurable fingerprints. The exosphere is the final frontier of a planet's atmosphere, a place where individual atoms drift so far apart that they barely interact. A place where an atom can escape into space with hardly any effort. This is where MAVEN listens. This is where it detected the whisper of hydrogen. That didn't belong to Mars. To understand how profound that is, you need to understand how comets work. Far from the sun, a comet is frozen and silent, a mixture of water ice, CO2 ice, methane, ammonia, dust, and organic molecules, all locked together. But as it approaches the sun, the ice begins to sublimate, turn directly from solid to gas. This releases dust. This creates a coma. This forms the tail. And, crucially, ultraviolet light from the sun breaks apart water molecules into hydrogen and oxygen. Hydrogen atoms, tiny, light, fast, are thrown outward, forming a gigantic invisible cloud that can stretch millions of kilometers. This hydrogen corona is what MAVEN detected as it swept across Mars. The enhancement wasn't random. It wasn't noisy. It wasn't solar activity. It matched the timing, geometry, and velocity of 3I Atlas's passage perfectly. Even more surprising, the enhancement was built gradually. It rose, peaked at closest approach, then faded, exactly as the models predicted. If cometary hydrogen had intersected the Martian exosphere, this data told a precise, undeniable story. Material from a different star system touched a planet in ours. Some of that hydrogen escaped back into space, free once again to wander the void for millions of years. But some of it is mixed with the thin gases of the Martian atmosphere. Some of it collided with native atoms. Some of it slowed down, joined the planet's inventory, and became part of Mars. Think about that. If a future astronaut scoops up Martian air for analysis, a few atoms in that sample may have been born under a completely different sun. And that's just hydrogen. Because MAVEN detected subtle increases in carbon and oxygen as well, elements that form the basis of organic molecules. Yes, 3I Atlas carried organics, and some of those organics reached Mars. It's important to be clear. This is not evidence of life, not even close. Organic molecules are not biological. They form naturally in interstellar dust clouds, on icy grains, in stellar nurseries, and on comets. But what their presence does mean is that the raw chemical building blocks of life do not belong to Earth alone. They travel between star systems. They wander the galaxy. They fall onto planets, and in this case, we caught one in the act. It's also worth asking what Mars did to 3I Atlas, because the interaction wasn't one way. Mars's gravity tugged on the comet, even if only slightly. A tiny alteration in the path, a minuscule change in velocity. But when you stretch that change over tens of thousands of years and light years of travel, that minuscule change becomes enormous. Mars changed the comet's future, and 3I Atlas changed Mars in the smallest yet most profound way possible. Both objects left fingerprints on each other. Both objects are forever altered, not dramatically, not visibly, but undeniably. And that brings us to one of the most fascinating questions. Did the comet truly change Mars in a lasting way? The conservative scientific answer is probably not in any measurable sense. The atmospheric additions were tiny. The effects would fade quickly, nothing you could detect centuries from now. But there's another way to look at it, a deeper, more philosophical way. If even a single atom from 3I Atlas reached the Martian surface and became locked in a grain of dust or frozen into polar ice, then Mars is now physically different from before. Not metaphorically, not symbolically, literally. The planet now contains matter from a star that is not our star. That is the definition of a permanent cosmic change. Some scientists even wonder if interstellar visitors like 3I Atlas have been passing Mars for billions of years. How much material has accumulated? Could Mars's soil contain a long, subtle record of interstellar chemistry, a cosmic archive? We don't have the instruments yet to answer that question. But the encounter with 3I Atlas, it's the first time we've ever had proof that the process actually happens. And it changes how we think about the origins of chemistry throughout the galaxy. As the scientific community analyzed the data from 3I Atlas, another group quietly watched the entire event with deep interest: the planetary defense teams. Why would a comet that didn't threaten Earth matter to the people responsible for protecting our planet? Because 3I Atlas was a real-world stress test, a chance to see if our detection systems could identify a fast-moving object from deep space, track it accurately, and coordinate global observations before it vanished forever. And the verdict was clear. We passed the test, but only just. Planetary defense isn't science fiction. It's a real field with real risks. Earth has been hit before, from the dinosaur-killing asteroid to the 2013 Chelyabinsk meteor that shattered windows across Russia. Most of the time, the threats come from familiar places: asteroids in predictable orbits, comets we've seen before. But interstellar objects, it is a completely different challenge. They come from any direction, they move fast, and we only see them when they're already inside our solar system. 3I Atlas behaved exactly this way. It was discovered only months before its close approach. Its speed was enormous, and its trajectory was unlike anything local to our Sunday. Planetary defense teams realized something important. If an interstellar object were ever on a collision course with Earth, we might only have 6-12 months of warning. That is not enough time to launch a deflection mission or build new spacecraft. We would have to rely entirely on whatever tools already existed in orbit or on Earth. 3I Atlas, without meaning to, exposed that vulnerability. It was harmless, but it showed us how quickly an interstellar visitor can appear, pass through the solar system, and leave forever. Scientists asked a sobering question. If 3I Atlas had been heading toward Earth instead of Mars, what could we realistically do? The answer is difficult, because objects from other star systems move too fast to intercept easily. Deflection strategies like kinetic impactors, gravity tractors, nuclear pushes, all require time. years or decades. Interstellar objects don't give us that. So instead of imagining dramatic Hollywood solutions, researchers focused on something practical: earlier detection. We need telescopes powerful enough to see these objects while they're still far beyond Pluto, when they're faint, cold, and barely visible. Projects like the Vera Rubin Observatory, the NeoCam infrared telescope, and future space-based survey missions are now being designed with interstellar detection in mind. Because 3I Atlas taught us that visitors from other star systems don't announce themselves politely. They just arrived. The 3I Atlas Mars event forced the international scientific community to act with unusual speed. NASA, ESA, CNSA, and observatories worldwide formed a spontaneous global network, sharing data, updating the trajectory, coordinating telescope schedules across continents. It was the closest thing to a planetary defense drill. We've never experienced an interstellar object. And it worked. But the success depended heavily on luck. Maven happened to be in orbit. Mars Express was still operational. Ground telescopes were positioned well. Skilled teams were awake and available. Future encounters may not be so favorable. The planetary defense community came away with a mix of pride and caution. Confidence, because the tracking was accurate, the predictions were correct, and the observing campaign succeeded. Humility, because Earth is still vulnerable to fast-moving visitors we may discover too late. 3I Atlas may not have threatened us, but it revealed the gaps we still need to fill before a different kind of comet tests our readiness again. And that leads to another layer of the story, one that had nothing to do with science and everything to do with human imagination. Within just a few hours of the first news reports announcing that 3I Atlas had passed close to Mars, the internet exploded with reactions, many fascinated, many confused, and some suspicious. Forums, social media threads, YouTube comments, conspiracy pages, and late-night podcasts all began spinning their own stories about what really happened. Some theories were harmless speculation. Others were wildly imaginative. A few became full-blown conspiracies that had nothing to do with science and everything to do with fear and misunderstanding. Why does this always happen whenever something unusual occurs in space? To understand that, we have to look at human psychology and why our minds leap to hidden meanings when faced with rare cosmic events. The idea that 3I Atlas might be an alien probe spread quickly online. Why? Because the human brain is wired to search for patterns, stories, and intentions, even when none exist. A visitor from another star system passing close to a planet sounds purposeful, even when it isn't. And in the absence of clear, simple answers, some people jump straight to dramatic explanations. The object came from interstellar space. It moved fast. It behaved differently than local comets. It arrived during a time when government operations were slowed by a political shutdown. These coincidences became fuel for wild narratives. The most popular conspiracy theory claimed that 3I Atlas wasn't a comet at all, but a spacecraft sent by an advanced civilization to observe Mars or Earth. People pointed to how unusual the comet's trajectory was, how quickly it appeared, and how little warning we had. But here's the truth. Every piece of evidence matches normal comet behavior, and none matches an artificial object. Its brightness increased because sunlight heated its ice. Its tail formed because water vapor escaped into space. Its path curved because Mars's gravity altered it slightly. Nothing accelerated, nothing changed course, nothing transmitted radio signals. There was no anomaly, except the one created by bad assumptions and half-understood science. Another theory claimed the U.S. government shutdown was intentional, a cover to hide classified information about the encounter. But in reality, the shutdown made NASA's job harder, not easier. Teams were stretched thin, schedules were messy, resources were delayed. If there had been something to hide, this would have been the worst possible time to try hiding it. And other space agencies in Europe, India, and China observed the comet openly. They shared their data publicly. A global conspiracy across every major space agency is not just unlikely, it's impossible. People are not drawn to conspiracies because they are true. They are drawn to them because they are exciting. A mysterious alien probe is more dramatic than a natural comet. A global government cover-up, it is more thrilling than scientists sharing data in journals. But scientific explanations are often quiet, patient, and gradual. Conspiracies are loud, fast, emotional, and built to go viral. Here's the part conspiracy theories miss. The truth is already astonishing. An interstellar comet, born around another star, carrying hydrogen, water, dust, and organics, from a completely different part of the galaxy, passed close enough to Mars that we could detect its chemistry in the Martian atmosphere. We witnessed two different cosmic histories intersect for just a few hours. We measured atoms that formed in a different solar system. We recorded hydrogen that had been frozen for millions of years, being released into our planetary neighborhood. Reality didn't need aliens or secret agendas to be extraordinary. Science doesn't take away wonder, it deepens it. When we understand what really happened between Mars and 3I Atlas, we don't lose the mystery, we gain the truth. And that truth is richer and more beautiful than even the best conspiracy theory. There is a quiet sadness in watching something rare drift away, knowing that the moment has passed and will never return. The encounter between 3I Atlas and Mars lasted only a few hours at its peak, just a small window in the endless flow of cosmic time. And then, just as quickly as it arrived, it began to fade. The world's telescopes kept tracking it as long as they could, watching the comet retreat toward the cold outer edge of our solar system. Its coma shrank, its activity slowed, its brightness dimmed. The visitor from another star was returning to darkness. As 3I Atlas moved beyond Mars, then beyond the orbit of Jupiter, and eventually past Saturn, it began the slow transition from a sunlit traveler back into a silent, frozen wanderer. Its water vapor jets weakened as sunlight faded. Its tail collapsed as particles stopped escaping. By the time it reached the outer solar system, it appeared in telescopes as a faint, shrinking point of light, almost indistinguishable from the background stars. Soon, even the most powerful observatories could no longer see it. And then it was gone, not destroyed, but simply beyond our reach. Based on refined trajectory calculations, the comet is now headed roughly toward the constellation Cygnus. But toward, it is a flexible word on galactic scales. The nearest stars in that direction, they are light years away. At its current speed, around 65 kilometers per second, it will take tens of thousands of years just to approach the outskirts of another star's gravitational influence. And even then, there's no guarantee it will pass anywhere near a planet. Most likely, 3I Atlas will continue drifting through space for millions of years until one day it passes within the range of another star system where another civilization, if one exists, might briefly detect its passage. Imagine that. A future astronomer on a distant world might study this same comet, wondering where it came from, what systems it passed through, and which planets witnessed its arrival. And they would never know that for a few short hours, in the year 2025, human eyes and human instruments watched it sweep past Mars. As the comet faded, astronomers around the world captured their last looks. Some images came from giant observatories like Subaru in Hawaii or the VLT in Chile. Others came from backyard telescopes, amateur astronomers who had followed the comet since the day of its discovery. Time-lapse videos showed 3I Atlas is moving slowly against the fixed stars, its brightness dropping night after night. The final recorded images showed almost nothing at all, a tiny speck of dim light on a long exposure frame. But for the people who spent months tracking and studying it, that faint speck held enormous emotional weight. It represented the end of something unique, something they might never see again in their lifetimes. Schools and universities began using the 3I Atlas encounter in science classes as a perfect example of how astronomy works in real time. Teachers explained how to calculate a comet's orbit, how spectrographs detect water, dust, and organics, how multiple space agencies coordinate to observe a rapidly moving object. Students ran simulations. They reproduced orbit calculations. Some even tried to trace the comet's path backward through the galaxy to guess its birthplace. For many young people, 3I Atlas became their first taste of what real scientific discovery feels like. Not something abstract and distant, but something is happening right now with real instruments, real data, and real mysteries. Public interest faded quickly as news cycles moved on to other stories. But for scientists, this was only the beginning. The images captured, the spectra recorded, the atmospheric measurements, the hydrogen enhancements, the dust analyses. These formed a treasure trove of information that researchers would study for decades. Just as we still analyze Voyager data from the 1,970 seconds, future scientists will analyze 3I Atlas measurements for many years to come. Because every interstellar visitor teaches us something new about how stars form, how planetary systems evolve, and how matter travels through the galaxy. As the world's telescopes went silent and 3I Atlas slipped into the outer dark, a new phase of the story began. The slow, careful work of turning raw data into understanding. Research teams across NASA, ESA, CNSA, and dozens of universities began analyzing every photon collected during the Mars encounter. Atmospheric changes, hydrogen spikes, organic traces, trajectory refinements, brightness curves, ion signatures. Every dataset told part of the story, but none of them told all of it. The encounter between 3I Atlas and Mars was massive in scientific significance, yet delicate and subtle in its physical impact. To truly understand it, researchers needed months, and in some cases, years, of patient analysis. Even from a distance, 3I Atlas was unlike any comet we've studied from inside our own solar system. The spectral signatures showed abundant water ice, complex carbon-based organics, carbon monoxide, carbon dioxide, unusual brightness asymmetries. But there were also strange details that scientists still debate. Brightness variations. The comet did not brighten in a smooth, predictable way. It showed patches of active jets, regions where ice vaporized explosively as sunlight struck the surface. These jets revealed a rotating, uneven world, a frozen relic from a completely different stellar nursery. Organic molecules. Spectra hinted at complex organics, precursors to amino acids and nucleobases, the same molecules that form the foundations of life on Earth. This does not imply life, but it does imply chemistry that could support life under the right conditions. Compared to Oumuamua, 2017, and 2I, Borisov, 2019, 3I Atlas behaved more like a classical comet, but with a richer chemical signature and more vigorous activity. In many ways, it was the most informative interstellar object ever observed. A comet like 3I Atlas, it is not just a piece of ice and rock. It is a time capsule from the era when its home star formed. Its atoms were forged in a completely different environment, around a different sun, from a different cloud of gas, shaped by magnetic fields we will never witness. Inside its nucleus are frozen patterns, like fingerprints, of chemical conditions from a star system we will never visit. Every interstellar comet is a messenger. A letter from another world, written in chemistry instead of ink. This is one of the most fascinating, yet unresolved questions. Trajectory models trace its incoming path toward the general region of the Lyra-Cygnus area. But this region contains thousands of stars. The Milky Way rotates, stars drift, clusters disperse. Over millions of years, the star system that birthed 3I Atlas may no longer exist in its original form. Scientists consider three main possibilities. It was ejected from a stable planetary system. A giant planet or brown dwarf might have slingshotted it out during early planetary formation. It originated in a young stellar nursery. Maybe it formed in a now dispersed cluster of stars where hundreds of suns were born at once. 3. It was freed from a dying star system. If its parent star went supernova, stellar winds could have ejected comets by the billions. We may never know its exact birthplace, but that mystery, it is part of the beauty. As 3I Atlas passed Mars, the red planet's thin atmosphere responded in ways we had never observed before. MAVEN detected a clear enhancement in hydrogen concentrations at altitudes aligned with the comet's trajectory. This was the critical evidence proving cometary material had actually reached Mars. Other enhancements followed: faint oxygen spikes, carbon signatures, ultraviolet scattering changes, temporary exospheric distortions. None of this was dramatic enough to shift the global climate or alter weather patterns, but it was dramatic enough to prove something profound. Entered the Martian atmosphere and stayed there long enough to measure ****. This alone rewrites parts of planetary science. Did 3I Atlas permanently alter Mars? In a measurable sense, probably not. In a literal sense, yes. If even a single atom from the comet landed on the surface or became trapped in the atmosphere, then Mars is now compositionally different than it was before. That difference is tiny, but real. Humans tend to think significance requires a large scale, massive impacts, huge changes, visible scars. But in the universe, the smallest exchanges carry the deepest meaning. A trace of hydrogen from another star. It is now part of Mars. And that is astonishing. Can we detect interstellar atoms on Mars later? This question fascinated scientists long after 3I Atlas had vanished into the outer darkness. Could a future mission, a lander, rover, or sample return, ever detect a trace of material that came from another star? Could Perseverance or a future rover find an isotopic signature that does not match anything native to the solar system? The answer is complicated. Theoretically, yes, you could detect isotopic anomalies that point to an interstellar origin. Practically, almost certainly not. Mars has been bombarded by cosmic dust for billions of years. Every meteorite that hit Mars contained grains from ancient supernovas, distant nebulae, and old star systems that drifted into the early solar disk long before Earth formed. Mars is already a museum of interstellar material. Trying to isolate a specific grain left behind by 3I Atlas would be like trying to find a single raindrop in the entire Pacific Ocean. But again, the scientific impossibility does not diminish the philosophical significance. Mars has been touched by another star. And that matters. Could 3I Atlas teach us about other solar systems? Absolutely. In fact, the chemical signatures detected during the Mars encounter They are already influencing theories about how planets form around other stars. Spectra showed that the comet had abundant water, complex organics, carbon monoxide, carbon dioxide, rocky dust, and variable outgassing behavior. This suggests that other star systems likely form icy bodies, much like our own, a powerful hint that solar systems across the galaxy share common chemistry. We learned that water is not rare, organic molecules are not rare, comet activity is not rare, gravitational ejection is not rare. The galaxy makes comets the way Earth makes sand grains, billions upon billions of them. Each one a wandering seed of chemical complexity. Scientists have long debated whether life on Earth originated entirely here, or whether some ingredients came from beyond the solar system. The 3I Atlas encounter did not prove anything definitive, but it strengthened a compelling argument. Organic chemistry. It is not a local phenomenon. It is universal. Interstellar comets demonstrate that the building blocks of life can travel between stars for millions of years before being deposited onto the surface of a planet. Could life's chemical seeds be exchanged across the galaxy? Could planetary systems share ingredients the way winds share pollen? Scientists call this idea galactic panspermia. It does not require life to survive long journeys between stars. It only requires simple molecules, nitriles, hydrocarbons, organics, to survive inside comets as they travel. And we have now seen that such molecules do survive. The universe may be far more connected than we ever imagined. Did 3I Atlas change Mars forever? This debate sits at the heart of the story. Did the comet fundamentally change the planet? Or did it merely brush past without leaving anything meaningful behind? Let's break it down. Measurable change? No, nothing we can detect today shows permanent alteration. Physical change? Yes, because atoms from another star entered Mars's atmosphere, and some likely settled. Philosophical change? Absolutely yes. Because Mars is now part of a cosmic story, much bigger than the solar system. For the first time in history, humans witnessed a direct exchange of matter between worlds from different suns. That event cannot be undone. Mars changed the 3I Atlas too. During the encounter, the planet's gravity altered the comet's trajectory, subtly but permanently. This means that when 3I Atlas eventually wanders near another star system, tens of thousands of years from now, its path will have been shaped, in part, by its brief dance with Mars. Two worlds from two different suns influenced each other. Tiny changes, but real ones. And that, it is cosmic poetry. The encounter with 3I Atlas also became a test for Earth's planetary defense systems, even though the comet posed no threat to Earth. Why? Because interstellar objects arrive fast, arrive from unpredictable angles, and are extremely hard to detect early. 3I Atlas demonstrated that. Detection pipelines work. The rapid trajectory calculation works. Global coordination works. Spacecraft retasking works. But it also showed how much we still lack. Early warning infrared telescopes, dedicated interstellar object missions, rapid launch capabilities, long-term tracking systems. If an interstellar object were ever on course to hit Earth, our response window might be measured in months or even weeks. That realization changed how space agencies think about future threats. After its close pass with Mars, 3I Atlas continued moving outward, away from the Sunday. Its speed, about 65 kilometers per second, was far too high for the Sun's gravity to capture. So the Comet is now on a one-way path back into interstellar space. In a few decades, it will pass beyond Pluto's orbit. In a few centuries, it will leave the Oort cloud behind. And then, for tens of thousands of years, it will travel silently between the stars, a frozen traveler carrying oxygen, water, nickel, and the chemical fingerprints of our solar system. Where will it go? We don't know. It could pass near another star in 1,000,000 years. It could wander alone through darkness for billions of years. Interstellar space is vast and mostly empty. But the comet will continue its endless journey, a messenger from a distant star that paused briefly to touch Mars and then faded away. Yes, and much more often than we once believed. Before 2017, humankind had never seen an object from another star. But then came 1I, Oumuamua, in 2017, 2I, Borisov, in 2019, 3I Atlas, in 2025. 3 interstellar visitors in less than a single decade. This changes everything. It means the galaxy is full of wandering objects, comets, asteroids, icy fragments, ejected from young star systems. Most will never come close enough to be detected. But the ones that do offer a rare chance to study chemistry from worlds we will never see. Some scientists estimate that tens of millions of interstellar bodies drift through our solar system every year, most too small or too dark to notice. The galaxy is not quiet. It is busy, restless, and constantly exchanging material between stars. The arrival of 3I Atlas marked the birth of a new scientific discipline, interstellar cometology. For the first time, researchers from different fields, comet science, planetary chemistry, astrobiology, spectroscopy, artificial intelligence, cosmic dust analysis, all came together to study a visitor from another star. This is science at its most exciting, because every interstellar object is a sample container from another world. Not a robot mission that took decades. Not a probe that we launched, but something that came to us. There is a reason this event captured the imagination of scientists, philosophers, and the public, because it forces us to rethink the story of life. Life may not begin isolated on a single planet. It may begin in the spaces between stars, in cold molecular clouds, in icy comets drifting for ages, in grains that survive supernova shockwaves. When these grains enter a young solar system, they dissolve, react, and seed planets with chemicals they need to evolve. In this view, life is not a local accident. It is a galactic process. Planets are simply bowls that catch falling ingredients. The universe may be filled with the same recipe because it is the first time in human history that we witnessed. This cosmic recipe is being delivered to a real planet in real time. We were there to see it happen. We had a spacecraft watching every moment. We had telescopes measuring every molecule. We had instruments confirming water, nickel, cyanide, the raw ingredients of chemical evolution. This wasn't something that happened billions of years ago on early Earth. It happened right now, in our century. And when SpaceX robots reach Mars in 2027, we may witness the next step, the mixing of heat, ice, organics, and catalytic metals in machines designed for industry, not chemistry. Mars may become the laboratory for a cosmic experiment older than Earth and larger than the Milky Way. By early 2026, the world's space agencies will finally release the processed data from the October 2025 encounter. This data includes ultraviolet readings from Mars Express, spectrographic scans from MRO, methane and gas signatures from India's MOM, high-speed plasma interactions, thermal behavior of the comet's tail. This will be the first time we see the complete picture of how 3I Atlas behaved during the Mars flyby. Scientists expect to learn how the comet's water outgassing changed over time, how nickel abundance spiked during peak activity, how cyanide emissions doubled every 2 weeks, how plasma tail particles interact with Mars. All of this will confirm whether the comet delivered more material than expected or less. And this data will decide where future robotic landers should dig. In September 2026, a historic launch window opens. SpaceX plans to send multiple robotic missions directly to Mars. Not one rover, not two, but a fleet of robots designed to dig into the regolith, melt ice, extract water, produce fuel, build early infrastructure, begin automated construction. These robots, the Optimus M class, are upgraded versions of Tesla's Optimus robots, adapted for Mars, radiation hardened, thermally insulated, dust resistant, fully autonomous. And most importantly, they use machine learning to optimize tasks based on efficiency. This means they will not choose locations based on chemistry. They will choose them based on results. If nickel-rich soil produces more water because of catalytic effects, the robots will choose that soil again and again and again. A feedback loop will begin. Between March and May 2027, the first fleet of SpaceX robots will land on Mars They will target the southern mid-latitudes, the exact regions where Mars holds shallow, accessible ice, and where HCN may have been deposited during the comet encounter. Once active, the robots will begin drilling, heating soil, capturing steam, filtering water, storing it, splitting water into hydrogen and oxygen. This is where the story becomes unexpected, because heating that soil does not only release water, it releases cyanide, it releases organic dust, it releases nickel particles, all inside hot metallic chambers. These chambers are perfect environments for catalyzed reactions. This is where the chemistry of 3I Atlas meets the technology of SpaceX for the first time. Within months of beginning operations, the robots will send back unexpected chemical data. Engineers may notice unusual carbon levels, nitrogen contamination, strange organic residues, catalytic patterns, changes in extraction efficiency. At first, these signs will be treated as normal dust or machine contamination. But slowly, patterns will emerge. Anywhere the soil contains refined nickel, the efficiency improves. Anywhere the soil contains frozen cyanide, organic residues increase. The AI will notice these patterns, even if humans don't. And because AI is designed to seek efficiency, it will choose the soil that performs best. That soil will be the soil touched by 3I Atlas. By late 2027, chemical labs on Earth will begin analyzing data packets from the extraction chambers. The results will surprise everyone. The chambers will contain nitriles, amino acid precursors, simple organics, polymer fragments, strange nitrogen-rich chains. Not life, not cells, not biology, but chemical structures more complex than the soil they were extracted from. These structures will form only when water ice is heated, cyanide is present, nickel is present, UV or thermal energy is applied. In other words, the exact conditions created inside the robot's industrial machinery. Robots built to extract fuel will become accidental laboratories for prebiotic chemistry. By 2028, the first peer-reviewed papers will be published. They will describe unusual nickel to iron ratios in Mars soil, cyanide contamination in frozen layers, catalytic reactions inside the extraction chambers, unexpected organics forming during processing. At first, scientists will argue about contamination, measurement error, or faulty sensors. But after repeated tests, consistent data, and multiple robots showing identical results, the scientific community will accept the truth. 3I Atlas changed the chemical landscape of Mars. And humans, through the robotic industry, activated that chemistry. By 2028, it will be clear that Mars is no longer the same planet it was before the 3I Atlas encounter. Nothing dramatic will appear on the surface. No glowing minerals, no visible changes, no new colors. The transformation is quiet, chemical, invisible. But it is real, and it is deep. Mars now contains refined nickel has never been seen in nature, hydrogen cyanide locked in ice, new organic compounds forming underground, catalytic combinations that did not exist before. For billions of years, Mars was a cold desert with slow chemical activity. Now, for the first time, the planet contains the ingredients for rapid chemical complexity. The key discovery of 2028 will not be what the comet delivered, but what the robots accidentally activated. Inside extraction chambers, the combination of metal heat, high-pressure steam, nickel catalysts, cyanide vapor, residual carbon, UV light leaks created a perfect environment for complex chemistry. Every chamber on every robot becomes a small, hot, metallic microenvironment, very similar to some theories of how early life began on Earth. Scientists will not say, "This is life." They will say, "This is prebiotic chemistry, accelerated by artificial machinery." For the first time in human history, technology and chemistry have combined to create something nature alone did not. One of the most fascinating and unexpected parts of the story will come from the robots' machine learning systems. These systems were designed to maximize efficiency, not understand chemistry. But by tracking thousands of samples, the AI discovers nickel-rich soils give faster water output, cyanide-rich ice changes the chamber temperature, organic residues improve filtration efficiency, nitrogen-rich polymers increase equipment strength. The AI does not know why these effects happen, but it learns to prefer these materials. This creates a feedback cycle. Robots select nickel-rich soil. Heating this soil releases cyanide. Cyanide reacts with carbon. Organic residues increase performance. AI prefers these locations again. A self-reinforcing system begins, a loop of chemistry and optimization with no human intention. By late 2028, labs on Earth analyzing samples notice something unusual. Some organic molecules become more complex after repeated cycles inside robotic machinery. Not because of biology, not because of replication, but because every time the robots process soil, they add heat, pressure, nickel, cyanide, carbon, UV exposure. This combination encourages molecules to link together. Scientists call this chemical evolution, the step before true biological evolution. It is the same kind of the chemical step that may have occurred on early Earth, but stretched over millions of years. On Mars, robots compress that chemistry into months. By 2029, robotic manufacturing begins producing a strange new category of Martian materials. Metal alloys become richer in nickel. Polymers contain nitrogen-doped chains. Panels and casings change color slightly due to organic residues. Engineers will report improved structural strength, altered brittleness, unusual resistance to thermal cycling, unexpected crystallization patterns. These materials come from the soil itself, soil changed by the comet. Each new generation of manufactured parts contains traces of the chemistry activated by the robots. In a quiet, almost invisible way, Mars begins producing its own hybrid materials, half natural, half artificial, half cosmic. By the end of the decade, scientists will realize that Mars has become something new. Not alive, not biological, but something closer to a chemical network powered by interstellar materials, robotic machinery, AI optimization, catalytic metals, repeated thermal cycles. This system grows as more robots operate. More robots means more processing. More processing means more reactions. More reactions means more complex molecules. And those molecules change the materials used to build the next generation of robots. A loop begins, a self-amplifying cycle of chemistry and technology. Something no planet has ever seen before. By the early 2032, scientists will debate a new question. Are humans changing Mars, or is Mars changing us? The answer will be both. Because for the first time in history, human technology and interstellar chemistry have merged to create a new kind of planetary process. This moment will be recognized as one of the most important in the history of space exploration. By now, scientists around the world will begin asking a question that feels strange, but impossible to ignore. Is this how life begins? Not life as in cells, organisms, or biology, not something growing on the Martian surface, but life in its earliest form, the raw chemistry that leads to complexity. Because Mars now has catalytic nickel, stable cyanide, water ice, organic chains, pressure and heat cycles, UV radiation, and continuous robotic activation. These are the same ingredients many scientists believe were present on early Earth before biology. The difference is, on Earth, this took millions of years. On Mars, robots will compress that chemistry into months. As the 2032 begin, Mars becomes more than a place to explore. It becomes a laboratory, a place where interstellar chemistry meets human technology. NASA, ESA, ISRO, and SpaceX will all begin sending specialized equipment to examine nickel reactions, cyanide deposits, organic residues, nitrogen-doped polymers, mineral changes in soil. International teams will model the strange chemical cycles happening inside the robotic extraction systems. Some labs will reproduce these reactions on Earth, inside heated metal chambers filled with Martian regolith simulants, added cyanide, nickel catalysts, UV lamps. Every experiment will show increasing complexity after repeated cycles. Scientists will call this sequential catalytic evolution. Focus will shift to the ancient southern highlands, Terra Sirenum and Terra Chimeria. These regions have the strongest crustal magnetic anomalies on Mars. These magnetic anomalies acted like funnels during the comet flyby, pulling nickel ions toward the surface in concentrated patches. Robots operating here will produce the most unusual chemical residues. Soil from these regions will contain nickel-rich particles, oxidized iron, frozen cyanide, carbon dust. This combination, it is rare in nature. But on Mars, it becomes common because of the 3I Atlas event. This region becomes the chemical heart of the new Martian ecosystem. Meanwhile, mid-latitude and polar ice contain cyanide delivered by the comet. These deposits have stayed frozen for centuries. But once robots begin melting ice for water extraction, the cyanide is released into heated chambers. And this is exactly when prebiotic chemistry begins. Cyanide reacts with ammonia, carbon compounds, nickel catalysts, trace methane, warm steam, forming amino acid precursors, simple nucleobases, organic chains, nitrogen-rich polymers. These are not alive, but they are the same kinds of molecules found in early Earth environments before life existed. This period marks one of the most profound scientific turning points of the century. For the first time, cosmic chemistry and human industrial processes combine in a feedback loop. Every robot heats more regolith. Every chamber creates more reactions. Every batch leaves behind more complex residues. Every data packet teaches AI to prefer nickel-rich soil and cyanide-rich ice. Every cycle generates more complexity. The system grows, not by intention, but by efficiency. Scientists will start calling this the Martian Cyber-Chemical Network. By 2032 or 2033, universities will begin forming new research branches: interstellar chemistry, machine-activated prebiotic systems, planetary catalytic networks, synthetic geochemistry, astro-industrial evolution. Funding agencies will direct resources towards studying chemical evolution, nickel-catalyzed organic synthesis, cyanide polymerization, hybrid mineral-organic reactions. Mars becomes the first place in human history where these phenomena can be observed in real time. As data arrives from Mars each year, scientists will slowly reshape their entire view of how life begins. For decades, we believed life had to start in warm oceans, or volcanic vents, or lightning storms. But now, the evidence suggests another possibility. Life may start in places where chemistry and energy come together repeatedly, regardless of biology. On Mars, the energy source, it is not geothermal heat, not volcanism, not sunlight. The energy source is human machinery. Heat, pressure, metal, steam, all the ingredients for rapid chemical evolution. This idea will completely transform the field of astrobiology. Months after 3I, Atlas passes Mars, as researchers sift deeper into the mountains of data from MAVEN, MRO, Mars Express, and the surface rovers, a new anomaly appears, something nobody expected. It doesn't come from the atmosphere, not from the comet tail, not from ultraviolet signatures. It comes from the ground, specifically from thermal readings taken by Perseverance inside Jezero crater. These readings show a repeating thermal pattern that shouldn't exist. A wave-like temperature fluctuation in the soil that cycles every 19 minutes. Not driven by sunlight, not driven by wind, not driven by changes in rover operations. Something in the soil is heating and cooling in a rhythm. Scientists call it the 19-minute thermal pulse. At first, they assume it's an error. A sensor glitch, calibration drift, data compression artifact. But then, the same pattern appears in Sherlock readings, pixel mineral scans, RIMFAX ground-penetrating radar. 3 different instruments detect the same cycle, all synchronized, all repeating, all coming from the upper 2-4 centimeters of Martian regolith. When the data reaches Earth, researchers freeze. Nothing in geology creates a stable 19-minute heat cycle. Nothing in Martian weather operates on that timescale. No robot system is heating the ground in this area. So, what's causing it? Eventually, one explanation emerges, and it shocks the entire field. Some researchers propose that the nickel cyanide organic mixture in the soil might be acting like a chemical oscillator, similar in concept to the Belousov-Jabotinsky reaction, oscillating redox systems, enzymeless metabolic cycles. Except this one is running inside Martian soil with interstellar molecules as the fuel. And here's the key insight. Oscillating chemistry is the first step toward self-organizing systems. Not life, not biology, not cells, but chemistry that runs in cycles, responds to energy, and stabilizes itself into repeating rhythms. This is the exact kind of behavior that early prebiotic Earth showed before life emerged. Next, teams re-examining Mars Global Surveyor data notice something else. Jezero crater sits on the edge of one of Mars's ancient magnetic anomalies, a leftover pocket of crustal magnetization, billions of years old. During the 3I Atlas flyby, this region would have acted as a natural magnetic trap for charged dust and ionized organic particles. Meaning, Jezero was one of the places most heavily dusted by interstellar material during the encounter. Combine that with melting ice inside rock pores, nickel catalysts from the comet, and robot-generated heat. And suddenly, the 19-minute oscillation makes sense. Something in the soil is cycling energy through chemical reactions triggered by the comet material. Here's the most astonishing part. The oscillations weren't present in earlier mission data. They begin only after the comet flyby, which means this chemical cycle is new, triggered, initiated, or amplified by interstellar chemistry. Mars didn't wake up, not in a biological sense, but its surface chemistry became active in a rhythmic, self-sustaining pattern for the first time in recorded history. Some researchers panic, some celebrate, some deny the findings. A few private messages leak. This can't be natural. We are watching prebiotic chemistry begin. We need to slow down robotic extraction. What if we triggered something we don't understand? Most scientists agree on one thing. This is the most important planetary science discovery since the detection of exoplanets. Because oscillating chemistry is not random. It is structured, predictable, evolving. And on Earth, every known pathway to the origin of life begins with chemical oscillators. Within weeks, the scientific world splits into three camps. The caution group: we must not alter Martian chemistry further. Stop all heating and extraction experiments. The exploration group: study it aggressively before the cycle collapses. The origin of life group: this is the first direct evidence of prebiotic processes on another planet. The media, sensing the scale of what's unfolding, begins calling the discovery the Martian pulse. For the first time, humans witness a chemical system on another planet that behaves like early Earth chemistry. Not alive, not growing, not intelligent, but moving in cycles, in rhythms, in pulses. Exactly the way pre-life chemistry behaves before crossing the threshold into biology. It all started because something from another star brushed past Mars for a few hours. And now, scientists realize we may be watching the first spark in a planetary chemical awakening. As 3I Atlas moved farther from Mars, the comet began dimming again. Its coma shrinking, its tail fading. The dramatic interaction that had lit up instruments across multiple planets was over. But for scientists, this was when the real work began. The data flood was immense: ultraviolet signatures, high-resolution images, atmospheric readings, plasma measurements, dust particle models, and every one of them needed careful analysis. Observatories across Earth began releasing their final recorded frames: tiny flickers of light, smudges against dense star fields, growing dimmer each night. Soon, the comet would pass the limit of Earth-based telescopes. And then it would be gone. Gone for good. Gone back into the cosmic dark where it came from. Gone on a journey no human spacecraft had ever followed. But what did the departure mean? And what, if anything, did 3I Atlas leave behind? Long after public excitement faded, research teams were still pulling images frame by frame from spacecraft radar logs. These final frames were faint, almost ghost-like, but they were precious. The tail structure changed rapidly as the comet cooled. The solar wind altered the direction of its particle stream, and the coma lost brightness as outgassing slowed. Each of these details helped answer key questions. How active was the nucleus? How fast was the comet losing mass? What was the ratio of water to carbon dioxide? Did it contain exotic ices rarely found in our system? One NASA researcher described these late-stage images as watching a candle extinguish in slow motion, except the candle was older than human civilization, end quote. With the encounter complete, 3I Atlas was officially on an escape path. It would leave the solar system entirely, never returning. The gravitational tug from Mars, though tiny, altered its outbound direction by a measurable amount. This mattered because over tens of thousands of years, even a small change compounds into enormous shifts. Trajectory models suggested the comet was now aimed toward the general direction of Cygnus, the Swan constellation. Not toward any specific star, but toward a region with thousands of possibilities. It would take 20,000 plus years to reach the outer edge of our sun's influence. Another 40,000, 100,000 years before drifting near another star system, and likely never entering another planetary system closely again. Most comets pass through the galaxy unnoticed. 3I Atlas was one of the lucky ones we saw it. We measured it. We documented its fingerprints. As the comet faded, astronomers worldwide began sharing their final datasets. Charts, spectral lines, brightness curves, orbital simulations posted in Slack groups, private servers, and preprint archives. None of these documents made headlines, but they helped decode the comet's chemical structure. High water content, organic compounds, carbon chains, dust patterns consistent with ancient star-forming regions. Some spectra hinted at isotopic ratios not matching our solar system. Proof, hard proof, that 3I Atlas was built under another sun. One astronomer wrote, "We were looking at the chemical memory of a star that may no longer exist." End quote. Schools and universities turned the 3I Atlas event into a case study. Teachers downloaded raw data from NASA archives and let students plot its trajectory, calculate its speed, analyze spectrographs, compare it to solar system comets. For many students, this was the first time astronomy felt real. Not diagrams in a textbook, but a cosmic event they lived through. Some classrooms held night viewings when the comet was brightest. Kids stood on playgrounds pointing telescopes upward, not fully understanding the science, but feeling the wonder anyway. Those children will remember that night for the rest of their lives. Some will become astronomers because of it. Some will become engineers. Some will simply never forget the feeling of witnessing something ancient and impossible streak across the sky. Despite thousands of observations, many questions remained. Where exactly did 3I Atlas originate? We know its direction of arrival, but stars drift over millions of years. Its birthplace may no longer exist. How old was it? We estimate millions of years, but it could be tens of millions or hundreds. Will it ever interact with another world? Statistically, no, but the galaxy is unpredictable. Did Mars gain any lasting chemical trace? Likely yes, but too faint to ever detect now. Could interstellar organics matter for life? Not for Mars today, but billions of years ago? Possibly. For centuries, humanity believed solar systems were sealed boxes. That material from one system stayed in that system, that only light, not matter, traveled between stars. 3I Atlas proved otherwise. It showed that solar systems bleed into each other. Planets get dusted with alien chemistry. Interstellar exchange is real. The galaxy is connected in ways we never imagined. Is the hydrogen detected in Mars's atmosphere? It originated around another star. That alone changes the story of planetary science permanently. 3I Atlas gave us a glimpse into another star's chemistry. Proof of interstellar interaction, a real-time cosmic event recorded from multiple planets, a test of global scientific coordination, inspiration for future missions, new questions that will fuel decades of research. It also gave something intangible, a reminder that the universe is not dead, not static, not distant. It is alive with movement, alive with ancient travelers, alive with stories written in dust and ice and starlight. Eventually, the comet became too faint to detect. First, small telescopes lost it, then mid-range observatories. Finally, even the largest instruments on Earth lost the signal. One night, a researcher checked the final coordinates, stared at the silent frame, and said quietly, "It's gone." 3I Atlas had left the solar system behind, but its impact, scientific, emotional, philosophical, was only beginning. When the dust settled, both literally and scientifically, researchers began a long, slow, intensely technical process of decoding what 3I Atlas had left behind. Months passed. Then more months. Teams across the U.S., Europe, India, China, Japan, and South America all contributed to one of the most detailed interstellar encounter analyses ever performed. And slowly, like a cosmic puzzle forming piece by piece, a picture emerged. MAVEN's ultraviolet spectrograph detected something extraordinary, a temporary spike in hydrogen density in Mars's exosphere. This was the smoking gun, the direct proof that scientists had hoped for. Hydrogen atoms from 3I Atlas actually reached Mars, meaning the comet's hydrogen corona was enormous. Its water ice was sublimating rapidly. Interstellar water vapor brushed against Mars. Mars's atmospheric chemistry shifted, even if temporarily. The spike lasted only hours, but the event was historic. Never before had humanity measured interstellar material touching a planet in our solar system. Hydrogen wasn't alone. MAVEN detected faint but real increases in oxygen, carbon, trace ions from cometary organics. These signals lined up exactly with the moment Mars passed through the outer layers of 3I Atlas's coma. This meant something profound. Atoms born around another star were now mixed into Mars's atmosphere. Mars, a world over 4 billion years old, had just been chemically touched by a visitor from beyond the Sunday. The most astonishing discovery came from combined spectral data. Carbon-based organic molecules were present in the coma. Expected? Yes. But these were not identical to organics found in solar system comets. Their isotopic fingerprints were subtly different, meaning they formed in a stellar environment unlike our own. Some researchers called this alien organic chemistry, not life, but foreign chemistry. These molecules were formed in a cold nebula, hardened by cosmic radiation, preserved inside the comet for millions of years. A sample of another star's chemistry delivered to Mars. Mars Reconnaissance Orbiter revealed active jets erupting from the comet's cracked surface. These were not smooth or regular. Some burst violently, some sputtered, some shut off and flared back unexpectedly. These jets carried water vapor, dust, carbon compounds, icy grains, volatile gases. Every eruption added fresh material to the coma, and some of that material flowed across Mars's atmospheric boundary during closest approach. 3I Atlas wasn't a silent ice ball. It was dynamic, reactive, and alive in the scientific sense. Multiple observatories reported unusual brightness fluctuations not predicted by standard comet models. Possible causes included uneven surface composition, subsurface pockets venting irregularly, jets activating only on certain rotations, fractures opening and closing. These irregularities suggested something extraordinary. 3I Atlas was chemically and physically different from almost any comet we've studied. It behaved like an object shaped by a stellar nursery far from our own. After compositional analysis, scientists reached an almost poetic conclusion. 3I Atlas contained material older than our Sunday. Some atoms inside it were formed in stars that died before the sun was born, ancient supernova remnants, molecular clouds long gone. This made the comet a true galactic fossil. Not just a visitor, but a messenger delivering stories from worlds we will never see. Two scientific camps emerged. Camp A, nothing permanent happened. Incremental changes are too small to matter. Camp B, a permanent trace remains. Even one interstellar atom now part of Mars is enough. And because MAVEN detected hydrogen and oxygen from 3I Atlas, a permanent trace undeniably exists. It could be undetectable now, but real. Mars is now, in the most literal sense, slightly more interstellar than before. 3I Atlas proved something revolutionary. Planets can be chemically touched without impact. Atmospheres can blend at the edges. Interstellar dust can integrate into planetary chemistry. The event rewrote models of planetary isolation. For a few hours, Mars experienced contact with a visitor born under another Sunday. Where 3I Atlas is now. After passing Mars, the comet dimmed, cooled, lost its coma, slowed outgassing, faded beyond telescope detection. But trajectory data revealed its destination. 3I Atlas is heading toward interstellar space in the direction of Cygnus. In around 20,000 years, it will exit the heliopause. Beyond that, it becomes again what it has always been, a wanderer between stars, carrying with it a microscopic dusting of Mars, a cosmic exchange that will never repeat. As soon as news of 3I Atlas spread online, a second story began to grow, a story that had nothing to do with science. Social media lit up with wild claims. 3I Atlas is an alien ship. For Zenter, NASA is hiding something. The Mars encounter was planned. The comet changed direction on purpose. None of it had evidence. None of it matched the data. But it spread anyway. Why? Because the human mind seeks meaning, especially when something feels too rare, too perfect, too cinematic to be random. When an object from another star system brushes past Mars, the truth already sounds like science fiction. Some people simply want it to go even further. Scientists responded the only way science can, with transparency, method, and evidence. And the evidence was clear. 3I Atlas behaved exactly like a natural comet. No propulsion, no controlled maneuvers, no signals, no intelligence. Just physics, beautiful, complicated, ancient physics. But the misinformation wave taught researchers something important. When science encounters awe, myth always follows. The encounter became a planetary defense case study, not because 3I Atlas was dangerous, but because it arrived fast, unexpectedly, and from an angle that no standard survey was looking. Interstellar objects don't follow the neat, flat disk of the solar system. They come from any direction, at high velocities, and give us very little warning. 3I Atlas proved our detection systems work, but barely. Response time must improve. International coordination is essential. Planetary defense must include interstellar threats, not just local ones. Most importantly, we need earlier detection of interstellar visitors. Because not all of them will be harmless, and not all of them will miss. This realization accelerated plans for infrared deep sky surveys, autonomous telescopic networks, AI-driven orbital prediction, a rapid response mission for future interstellar objects. 3I Atlas was not a threat, but it was a warning, a rehearsal for something that could be. After the closest approach, the comet began to fade. Its coma shrank. Its jets quieted. Its brightness dropped off a cliff. One by one, telescopes lost sight of it. Even the big observatories, Keck, Subaru, VLT, eventually said goodbye. The last images showed nothing more than a weak, ghost-like smear moving silently toward the edge of the sun's influence. In a few thousand years, 3I Atlas will pass the heliopause and return to interstellar space. Forever. It will become what it has always been, a wanderer drifting between the stars, on a journey no human mind can fully grasp. Somewhere, someday, it may sweep past another planetary system. Perhaps an alien civilization will detect it. Perhaps they will wonder about the dust and ions adhered to its surface, tiny particles from Mars delivered across light years. A trace of our solar system riding a visitor to worlds unknown. For scientists, 3I Atlas was not just an observation, it was an awakening. It proved solar systems are not isolated. Interstellar chemistry blends with planetary environments. Worlds exchange material across the galaxy. It reshaped how we think about planet formation, organic chemistry, prebiotic molecules, galactic mixing, the origin of life. And perhaps the most profound realization, some of the material that helped spark life on Earth may have come from comets like 3I Atlas long before we existed. The story of life might not be local. It might be galactic. As the final data came in, as the last telescope released its last image, scientists around the world felt something unexpected, a sense of loss. It is strange to feel emotional about an icy object that never knew we existed, but humans form connections with the things they study deeply. 3I Atlas fascinated us, challenged us, united us, changed our understanding of cosmic exchange. And then it vanished. Not in violence, not in tragedy, just in distance. A traveler slipping back into darkness. But it left something behind, not on Mars, but in us. A reminder that the universe is alive with motion, filled with messengers from distant suns, and far more connected than we ever imagined. And so, as we close this chapter, we say farewell not with sadness, but with gratitude for the rare chance to witness a meeting between worlds. This has been Vertex, where we explore the mysteries of space, the evolution of science, and the cosmic stories that shape our future. If this journey moved you, leave a comment, like, and subscribe. Tell us, what do you think was the most extraordinary part of the 3I Atlas encounter? Until next time, keep looking up, stay curious, and remember, the universe is still full of wonders waiting to be found.